Thank you for the introduction, Volker. Is the mic on? Yes. My name is Oliver Hofmann from the Technical University of Graz. Maybe one more word about myself. In contrast to almost everyone else that you've heard so far, I'm not a die-hard method developer, but rather what you would probably call a power user of DFT codes. So what this means is that in my talk I want to focus much more on the in practice part, where in practice doesn't mean necessarily how it's implemented in practice, but what that means for you if you do a calculation in practice. Well, nonetheless, let's get started with the usual introduction. What we want to do, whatever we want to do with our calculation is we want to solve the Schrödinger equation. Where the wave function is basically given as a function of the nuclear coordinates and the electronic and spin coordinates. The Hamiltonian, as you all know, and as Hardy Gross has discussed and presented earlier, the Hamiltonian we can separate into contributions from the nuclei, the kinetic part, the kinetic part for the nuclei, the nuclear-nuclear interaction. We have the nuclear-electron interaction, the electron-electron interaction, and the kinetic part of the electrons. And as Hardy Gross has also said before, the full many-body solution is typically not a sensible or not attainable, or at least not easable. So we go through two important approximations. We invoke the Born-Oppenheimer approximation as our default approximation that we use basically all the time. And we assume that the electrons are in an eigenstate of the electronic Hamilton operator. What this means is we can separate nuclear and electronic coordinates. And this is what basically gives the outline of my talk, or how I structured my talk. I will first discuss how we can solve the electronic part and go through the self-consistent field method, discuss a little bit about density mixing and preconditioner, and later about why we can and should broaden the states, the orbitals. And then I'll talk a little bit about nuclear structure optimization. How do we actually find a sensible geometry? Where we'll focus on local structure optimizations, forces in DFT, and vibrations only within the harmonic approximations. Most of these parts will be discussed, at least from a theory perspective, in a little bit more details by later speakers. And that's also why I want to focus on more the practical implications. Good. The first question is, where are actually our electrons? We know that in density functional theory, all ground state properties are related to the electron distribution. So the electron density is a unique and good representation for our systems. And from this electron density, we can calculate basically any observable, such as the relative energies of conformers, dipole moments, reactivities, and so on. And this is where we then actually want to employ density functional theory. We use density functional theory in the Combs-Sham scheme, which means that we map the electron density onto effective one-particle orbitals, and the electron density is then given essentially as the sum over the square of the wave functions of these orbitals times their occupation. What we want to do is we want to determine, this is all just a repetition of what Hardy Gross has said in much more detail, and this was much more knowledge earlier today. We want to determine the orbitals or auxiliary variables such that the energy as a function of the electron density is a minimum, and such that the Hamilton operator that includes the electron density is consistent with the orbital that we get out of it. So how do we actually do this now in practice? There are, in principle, at least two different ways to achieve this. One is the so-called direct minimization, where you start from what is a reasonable guess and then you try to minimize the coefficient. And the second method, and that's the method that's de facto always used, is the so-called self-consistent field method. So how does the self-consistent field method work in principle? Well, as always, you need to start from an initial guess. for example, a guess of at least the electron density, because that's in the Hamiltonian. From this electron density, you can then calculate the electron, the potential. With the potential, you can construct the full Hamiltonian, solve the Schrödinger equation, or invoke the approximations that you want to invoke, and obtain eigenvalues, eigenvectors. The eigenvectors are your orbitals, and a new density. After that, the question is, are you converged or not? And what that means I will discuss on the next slide. But let's say yes, then we would be finished. Typically, after the first iteration, we will be not. And what that means is we need to update what has been our initial guess. We need to get a new density matrix, a new density. And for that, we will apply a mixer or a preconditioner. And with the updated density, we update also our potential, and then we close the cycle and go through it once again. And we go through these cycles repeatedly until we actually are converged and can answer this question with yes. Then we are finished. Now, one of the important questions that is, in my opinion, frequently neglected is, what does it mean that a calculation is converged? The simple definition is my calculation converged is that the property that I'm interested in does not change anymore. I could run more and more of my self-consistent field iterations and I would still get the same answer. Now, this is of course not an exact science. You always have to define a convergence threshold, and if you choose it correctly, you get a converged result. If you've chosen it too low, the convergence threshold, you will get a number that has a large error bar to it. You will get a very inaccurate result. You will still get an answer from your code. That's an important message, right? The code will tell you an answer, but that answer has not necessarily been stable because you never tried to basically run the next iteration in your SCF. Now, that's not how it's designed to work. But you will get a very inaccurate result. You could even set it much more loosely. Say you want to converge the change in the charge density to 10. Then you will be done in one iteration. But what you will get is basically a random number that is just defined by the initial guess that you used. So it's obviously important to use a converged result that is reasonably strict. You could, of course, also over-converge your result. That is, from a theoretical perspective, very nice. In practice, it's very nice if you do that. But in practice, a computation costs money. It's something on the order of 1 cent per CPU hour or so. And actually, you're wasting money with that if you do it if you go too strictly. Right? You need to do too many iterations, and well, the calculations takes maybe twice as long. It also wastes a big time of your human time that you invest in it. And if you over-converge it much too much, well, you run into numerical instabilities and probably get your calculation never to converge, meaning you never get a sensible result out of it. What you want to find in the end is the middle ground that gives you a stable, nicely converged result that doesn't take too much time. Let me briefly digress. What are the typical properties that we converge within our SCF cycle? Well, we're using here mostly FHI aims, so I use the 3 convergence parameters of FHI aims here as an example. We have the change of the electron density, we have the change of the sum of the eigenvalues, and we have the change of the total energy. These are typical convergence criteria, typical exit criteria for the SCF. I should emphasize at this point that there are, of course, many more exit criteria that you can invoke, and also in aims, but also in other codes. And this is also something that's important to bear in mind. Not all codes have the same convergence criteria implemented. Not every code can actually checks for the sum of eigenvalues. Most, of course, check for the change in the total energy. Right? The problem is when you look at these kind of exit criteria, that may be not what you're actually interested in. So say you place a large molecule on the surface and you're interested in the interface dipole. The interface dipole is not one of these properties that you actually have converged here. So you need to somehow make sure how these relate to each other. Okay. A second part that I wanted to say at this point is that not only do the objects differ between codes, but also the threshold for convergence is something that people tend to not think about too much, and they're often historically grown. I can just tell you as a part of an anecdote, I did my PhD already in Graz quite a while ago. I left Graz for basically half a decade. When I came back, people were still using the same input files that I had used back then. They were just copied. Of course, this is a very bad idea because I had used the input files already from my predecessor, so they were maybe 10 years old. And the convergence threshold that were placed in there were chosen such that the calculation will finish in time. It was not a good convergence threshold, it was just the best you could do 10 years ago. And the best you can do today is much better than the best you can do 10 years ago. So this is something you should think about when you choose your convergence threshold. So what are safe convergence thresholds usually? The problem is it depends a lot. Okay, Volker just tells me it's automated in Ames now. Maybe he can tell me more about this later. So I'll probably skip about that a little bit. Just let me still tell you that for these exit criteria that are implemented, what is a good convergence criteria depends very strongly on what you actually want to get out of your code. It's very easy if you want to get energies out of your code or dipole moments, in which case there's a relation to the electron density. But if you want to have force constants or something, the relation to the exit criteria may not be self-evident. The second problem with convergence threshold is that they're not necessarily transferable between different systems. So what works for a small system may not necessarily work for a larger system. The reason is just that you have, because of the approximations that are invoked, you have some numerical errors, so to speak. Well, you're just converge, say, the total energy to an accuracy of something that is sub-MeV. But if you use a very large system, the total energy convergence criterion that was nice for a small system will no longer work for a large system. Not all exit criteria are determined the same way across different codes, so they're not necessarily transferable between different codes, and sometimes not even transferable between different algorithms within the same code. Now that sounds very dire, but I should emphasize at this point that there was a recent study by Layagere, I hope I pronounce him halfway correctly, where he and actually a huge group of scientists have evaluated how comparable the results are between different codes. This is just an example for the PBE lattice constant of silicon, used across, I don't know, maybe 10 different codes or so. I don't remember exactly. What you can see from this graph is that in earlier times, the lattice constant could actually differ quite a bit. And nowadays, we have much more control about our approximation. We can, as I had just said, invoke much stricter convergence criteria. And if you actually go to over-converged convergence settings, the results are mostly code independent. You see that there is still some spread, but the spread is actually very, very small, and the precision of the code is now, I would say, extremely well. I should still emphasize at this point, it's good that all codes give, or most codes give, more or less the same result when you use over-converged settings. In practice, however, we will typically use under-converged settings, especially if you're interested in large systems where we probably cannot afford to go to the biggest basis set, to a fully converged k-point grid. And how these under-converged settings impact the accuracy of the code is something that is not as well known as implied by this graph. So the take-home message for convergence settings is, first, you should critically look at and probably converge your convergence parameters, not take them too strict because that wastes time, not take them too loose because you get inaccurate results. And the second take-home message is you should check how these convergence parameters actually affect the observable you're actually interested in at the end of your calculation. Good. Let's go back to the self-consistent field and start with the beginning, basically the initial guess, the density. How do we guess what the electronic structure of our system should look like? And why is this important? The reason why this is important is because for some reason it's frequently neglected that also the electronic structure or the electronic potential energy surface has multiple minima. Or my favorite example for this is actually oxygen, which is the gas that we all breathe. If we would just not care about spin and use just the default initial gas, which is, well, implied symmetrically, we would typically end up with an initial gas that is very close to singlet oxygen. And singlet oxygen is actually a stable solution on the potential energy surface. It's just not the correct solution for oxygen. Oxygen in its ground state is a triplet, as I assume most of you know. And that's good because if it was singlet, then it would react with organic matter without a large reaction barrier, and we would all burst in flames. Bad. Good. So what I want to say with this is basically before you start your calculation, you need to think about what is a good guess for the electronic structure and get a good idea. You can actually think about why it should be a triplet beforehand. You can get that from symmetry arguments, or you can test different starting points for the electronic structure and then see where you find the global minimum. I should emphasize also at this point that this is not only a side problem for oxygen or some other diatomic molecules. It's also a common issue in magnetic solids where it's not a priori clear what will be the correct or best or whatever spin moment. So how do we find a stable, reasonable, fast converging initial gas for our self-consistent field calculation? Maybe a historic initialization, I'm not sure if it's actually used anymore, is to initialize the wave function randomly. That is, you take your basis functions and you assign random coefficients to it and build from that the total wave function. The advantage of this approach is that it is really straightforward to implement. It's very, very fastly done very quickly, and that it's completely unbiased, which can be a good thing. The negative part, and that I think outweighs the advantages by quite a bit, is that it's far from the correct solution. It doesn't have any chemical motivation, so the initial gas will be mostly bogus. And if the initial gas is bogus, you will need a lot of iterations until you actually find in the end the correct minimum structure, electronic minimum structure in that case. And it doesn't account for the fact that the density varies most strongly near the nucleus. So it's mostly used in plane wave codes, if it's used at all, and it's sometimes still there as a backup method, but as I said before, I don't think it's actually used in practice a lot anymore. The second method that I want to introduce is the superposition of spheric atomic densities, which is, at least in band structure codes, the most common way to initialize the electron density. The idea is very simple. Let's say you have two atoms. You calculate the spheric density that atom A would have. You calculate the spheric atom density that atom B would have. And the total density is then just the superposition of these two. Also, this is reasonably straightforward to implement. All that you need is a solver that calculates the spheric atom density around each atom with a given functional. It's also okay. It's mostly sufficient. It will give you a reasonable electronic gas. But the electronic gas will not be very nice. Not necessarily. It may be still relatively far from what is actually the truth. And an additional problem is you don't have any control about which orbitals should be occupied. Right? And sometimes, well, especially if you want to change the initial gas, you want this control. Other disadvantages, more from a technical perspective, is you don't have a density matrix. You have to create a density matrix in the first SCF gas and no orbital coefficients. And another part is that atoms are not spherical objects, with a few exceptions. And that means if you actually want to calculate an atom from this initial gas, the initial gas will be very bad, and typically you will end up in the saddle point, or very often you will end up in a saddle point of the electronic potential energy surface rather than in a true minimum. I believe that later today in the tutorial there's an example that illustrates that very nicely. Still, it's, I think, in band structures the most commonly used method. It's used, for example, in AIMS, it's also used in WASP, and I'm sure it's also used in many of the other codes. The third method that I would like to introduce is the method that is most commonly used in chemistry codes, say Gaussian, turbomole, or whatever, and that is that you start from a semi-empirical method, such as the Hückel method. Hückel method is a very popular method in chemistry that basically starts from a linear combination of atomic orbitals. It typically employs a minimal basis set. The original Hückel method only accounted for the p orbitals of conjugated organic molecules, but it can of course be extended to any kind of orbitals. And then you construct the Hamiltonian via this equation. You have 1/2 k. K is just a constant. S is then the overlap parameter between two atoms. And then you have two parameters, HII and HJJ, which are predetermined for each element. That's a very simple Hamiltonian, and you can just solve this Hamiltonian. You don't even need to solve it consistently, because the result is not in the Hamiltonian itself. And then you get out all these orbitals. Here's the example for the benzene molecule. And you see, you populate the lower ones according to the number of electrons that you have in there. So benzene, for example, this is just the p electrons. There would be 6 electrons in there. You would occupy this orbital, and this orbital twice each. And from that, you can then construct the electron density. And that's the guess from which you then continue your calculation. That's actually, in my opinion, a very nice method, because you have a controlled occupation of the orbitals. So it gives you a lot of flexibility. And it directly gives you a consistent wave function and electron density. The reason why it's often not done is because they're just not parameters available for all possible elements, or at least that used to be the case. Maybe that has changed by now. And as I've said before, it is in fact used in systems that focus more on well, elements that for which parameters are available. So if you do something organic, and that's done in quantum chemistry. Okay. So let's say we have our initial guess, and now we've run through our SCF cycle the first time, and we got out our new electron density. The question is now, how do we update the electron density to our new guess? What will be our new guess once we know what the result would be from the initial guess? The naive approach would be that we just take the electron density that came out of our calculations. This is sometimes also called the naive mixing approach. So we basically replace the old density by the new density. And whether this is a good idea or not, I've just created a small animation for that. Let's assume we have a very good starting guess, which is what you can see on the left side here. This would be for an example of a hydrogen molecule. The distance is a bit overestimated. The correct distance would be 0.8 angstroms or so, and I calculated them at a distance of 1.5 angstroms, such that the effect that I want to show is nicely overrepresented. And then I projected the electron density into just one dimension. So here would be one nucleus, here would be the other nucleus, and this is then the distance along the connection of the two hydrogen atoms. And if our initial guess looks like this, which already looks very reasonable, and then we just take the output, well, you can't basically see the difference as the iterations go by. We're converged to the correct electron density very quickly. But as I've just said before, the starting guess is not always very good. Sometimes it's actually terrible. And this is what you can see here on the right-hand side. Here I've actually placed all the electron density on one of these two hydrogen atoms. And what's happening now, if you just take the naive guess, is that the electron density tries to go to the other atom all the time, every time. And I've stopped after 29 iterations because you can already see that this will never converge. Naive mixing is just not a good idea. In the best case, you get oscillating non-converging results. In the worst case, You can even get bistable results which appear to be converged but are not. This is something that you can see very nicely if you try to converge a silicon atom with LDA, for example. So what can we do instead? One method is the so-called linear mixing. The idea here is similar to the naive mixing. We just take the electron density that came out of our SCF cycle, but we don't take the electron density completely, but rather we see what was the change to the previous electron density, and we apply that in a scaled way. We apply some of the change and not all of the change. The parameter that I've used here to indicate how much we accept from this is called alpha. And here's again the example with the very bad initial guess, where I use essentially 30% of the new electron density. What you can see here is that from the very bad initial guess, we very quickly find a sensible and converged solution. Now, the problem is now that we have introduced a free parameter, and it doesn't necessarily work all the time, every time. Let's assume I had something larger coefficient, say 80%. Of course, 100% would again be naive mixing. But even with 80%, you can see that you very easily run into a bistable solution. Right? These are now 29 iterations, and you have seen that after the first few, you get an electron density where there's some electron density on one atom, more electron density on the other, which is obviously unphysical, but they move back and forth, and the calculation never gets to a good result. I could also reduce the scaling parameter significantly, say to only 3%, and start from my very bad initial guess. You can see that the first iteration has jumped, which is an artifact on how I calculated it, and then you see that very slowly we're getting to the right result. Again, I stopped after 29 iterations because I just made this graph for 29 iterations, but you can see that this will eventually go to the correct solution. The problem is it will take a long time to get to the correct solution. What I want to say with these examples is that unfortunately there is no ideal recipe to choose what would be a good mixing parameter. If you use a too large mixing parameter, you might go into bistability, and if it's too small, well, it will take a while. The advantage is it's yes, please.
What do you mean by guaranteed convergence if it can be bistable?
No, okay. I was just about to say that. If you use a mixing parameter that is small enough, you're guaranteed to eventually achieve convergence. You're not guaranteed to live long enough to actually see it happen, right? If it's infinitesimally small, it will eventually converge to the right result. You can show that mathematically, right? But it might take an unfeasible large amount of iterations.
So small enough in the sense of there is some small number such that...
Yes. Yes, there's some small number such that it will eventually converge, but the number of iterations will be more and more and more. There's also a different kind of mixing scheme that's called direct inversion of iterative subspace, or Pulay mixing. And the idea of Pulay mixing is a little bit different. What we do in Pulay mixing is basically we calculate what's called a residual or an error vector. So we calculate again the electron difference between the initial and the final guess. We do that for a number of iterations. And after a number of iterations, we combine these error vectors such that we try to predict the electron density where the next error vector would be 0. Right? This is what's shown here. We weigh them in a least square sense such that the next residual would be, if possible, 0. The IIS scheme or Pulay mixing is something that is very frequently applied, and it's also reasonably robust, but contrary to the linear mixing scheme, it will not converge always. And it's much more sensitive to the actual mixing coefficient that you imply. And it has an additional parameter, and the additional parameter is the number of steps that you use to predict the next electron density, or to predict the null error vector, if you want to. still, what you do in the end is you calculate the electron density by the previous electron density plus a mixed or a damped additional factor from the residual that you just calculated. Yeah, you use under relaxation, so to speak, similar to linear mixing. Ideally, this would be independent of alpha, and in contrast to linear mixing, which has a very strong influence, here indeed the impact of the under relaxation is a little bit smaller. It's still not negligible, I have to say, but here we can at least define some rules of thumb. You should take a mixing parameter on the order of 0.2 to 0.6 for insulators and much smaller on the order of 0.05 for metals. Although I should state here very clearly that this doesn't necessarily work always, and is not necessarily always the perfect case. Sometimes you just have to play with it. Yeah. The advantage is it's much faster than linear mixing. The disadvantage is there's no guarantee for convergence. But for all practical implications, this I should stress maybe some more, for all practical intents and purposes, also the linear mixing does not guarantee convergence unless you have a very small system where you can easily afford 1,000 iterations. If you can just afford 58 iterations or maybe 200 iterations, typically the Pulay mixing will be the faster way to achieve convergence, and is therefore also the default method that's used in almost any code that I know of, at least. Beside the mixing, there is a second part that is especially relevant to band structure code, and that's called charge sloshing. So what is charge sloshing? Let's assume we calculated our initial guess by a superposition of spheric atom densities, which means that here the electron density would be the same for all atoms. I've shown here a slab of, I think, aluminium, and a slab of aluminium means it has a surface on the top and it has a surface on the bottom. And the surface is a kind of defect, and obviously on the surface the electron density should be different from the electron density in the bulk. What will happen in the SCF is that there will be some kind of charge redistribution between the bulk-like inner part of the slab and the surface. And if you have what's called a stencil cell, that means you have a very long and thin slab, you can again get to the problem that the change of electron density is strongly overestimated, and the charge starts to bounce back and forth. It goes from the bulk to the surface and back into the bulk, or even between the surfaces back and forth. And this is a problem because the charge density difference is applied continuously across all parts of the system. And this can actually be solved, or it can be at least mitigated by what's called a preconditioner. The idea here is, in a manner of speaking, to Fourier transform the electron density difference and then project out certain components of it. Specifically, damp the long-range oscillations more than you want to damp the short-range oscillations. This is just to put it shortly, and I see that I have to hurry a little bit, so I go over this a little bit faster. We then apply this Pulay operator, if you want to, that again depends on the mixing parameter and what's called a screening parameter. This is what you put into Ames if you have preconditioner Kircher and then a number. This is then the screening parameter. And once again, the screening parameter, unfortunately, is a free parameter that you need to select somehow. And once again, unfortunately, there's no ideal choice for that. There's typically a default, but it's not guaranteed to be the best choice in any code. The best guess, or a reasonable guess, would be if you can get the screening parameter from the Thomas Fermi screening. That's basically the square root of the Fermi wave vector divided by pi. And that typically should give you a very good result for metallic systems. How much it helps you, I wanted to illustrate by this graph. This is again the electron density as a function of the iterations, with and without preconditioner. And what you can see here is that some iteration first starts to converge very nicely and then suddenly starts to slosh back and forth if you don't have a preconditioner. With the preconditioner, the long-range oscillation is damped, and it's damped sufficiently such that eventually we find convergence. Yeah. I'll just skip that at this point due to time and go to the third part that I would like to discuss for the electronic convergence, and that is the special problem of metallic systems. For metallic systems, one of the problems that you have is that you have a lot of states that are very close in energy. And, sorry? You have many states that are very close in energy. And every time you solve the self-consistent field, you might start to occupy slightly different orbitals or slightly different states at different k points. And that leads to probably not a noticeable change in electron density, not a noticeable change in the total energy, but it's still too large to actually achieve convergence. And one of the tricks that is commonly employed to still achieve convergence is to smear out the problem across different states by applying applying an occupation function, if you want to. Now, if we did our calculation exactly at 0 Kelvin, what Fermi statistics enforce, or what Fermi statistics imply, is that every state below the Fermi energy would be fully occupied, and every state above the Fermi energy would be fully empty. What we could do most easily is we could rather apply a Fermi function instead, which has this functional form, and that's basically taking some occupation out of the states below the Fermi energy and adding additional occupation above the Fermi energy. And the nice thing about using a Fermi function would be that you can also actually interpret the parameter that you put into as some kind of electronic temperature. I'm not saying that necessarily you should do that, but in principle you can do that. The problem here is, unfortunately, that that empirically this function turns out not to be ideal to achieve convergence, and other functions are much more conducive to that. What's commonly used is a Gaussian function that is still a little bit sharper than a Fermi function, and the third method that is very commonly used is the so-called Mass-Fessel-Paxton scheme. Mass-Fessel-Paxton scheme is shown here in orange, and it's a little bit peculiar in the sense that unless the other functions, it actually goes to occupations below, above 1 below the Fermi energy and below 0 for 0. I should maybe qualify that a little bit more. Mass-Fessel-Paxton schemes, which work according to this equation and include some spherical harmonics here, exist in different orders, first order, second order, and so on, and only the first order really goes above and below the boundaries of what you expect. But still sometimes, sorry?
What is the mean of negative inversion number?
There is no mean to that. No, there's no physical meaning to that. Right? It's just the integration of an orbital over the whole energy range would still be 1. There's still one electron that fits into an orbital. Right? And here you would basically over-occupy the orbital if it's at lower energy. Here you would under-occupy the orbital if it's at lower energy. So it's basically, a numerical artifact, if you want to. Similar to Mulliken charges, which you're probably familiar with. Also, Mulliken charges can give you charges that are above 2 or below 0 for a given orbital.
Sorry. If I understand correctly, the problem with not converging is that the orbitals change.
Yes.
Just if you occupy one orbital, it just goes up, and unoccupied goes down. So
yes.
Okay, so for the metals, we can use a Fermi function.
Yes.
But for example, if I have a semiconductor and some kind of heat, and I have two levels which are nearby from each other, and I had the same problem, I couldn't solve it by playing it, like you have two levels which are always in different. Is it okay? To use this mirroring, or?
I'm not sure what you exactly mean. If you have a semiconductor, you have a gap between occupied and unoccupied states.
If you introduce a defect,
yes.
you get some kind of electronic levels inside the band structure, which are deep electronic levels. For example, you have two electronic levels which are nearby each other. And actually, you get this like flipping all the time. You cannot reach the convergence. So what you should do at this type of situation? It is not a method.
I think technically you should reduce the broadening parameter until you do not get fractional occupations. because the defect, so I'm assuming the defect that you're having is a localized point defect.
Yes, yes.
And the state that is associated to that is an orbital. And an orbital is either empty or it's full. It's not fractionally occupied. Now, let me say a but to that. In density functional theory, it's totally okay to have fractionally occupied orbitals because these can be interpreted as a time or ensemble average. So, in principle, it's okay if you want to fractionally occupy this orbital. Yes, if you want to fractionally occupy this orbital and then interpret the result as ensemble average. However, you need to see if the observable that you try to deduce from the electron density that you have just produced is also something that gives you a reasonable result from an ensemble average. Let me give you an example. Let's say you have 2 molecules and 1 additional charge to that. Right? You could either have 1 molecule charged and 1 neutral, or you can have both half charged. In an ensemble average sense, both would be legal. If you now calculate, say, the vibrational spectra from these will give you different results. Right? Because either you get the charged plus the uncharged, or you get something that is in between. In the example that I just gave you, the 2 molecules, it's not okay to have fractional charges. If you want to calculate, say, a phonon spectrum from your charge defect, or a partially charged defect, I guess you will get the wrong result. And you should actually get to a solution where you have a very strict function. It's either occupied or it's non-occupied. It's either in the band gap or it's outside the band gap.
Yeah, but for example, you can have a Jahn-Teller effect.
You can have, sorry?
Jahn-Teller effect, the symmetry breaking, and two, for example, generate.
Is Halicross still here? If I remember correctly, Jahn-Teller effects are not correctly described in the Born-Oppenheimer approximation. Can somebody comment on that? Who is more knowledgeable than I am? I think Jahn-Teller effects cannot be described correctly within the Born-Oppenheimer approximation, so you have a different problem here.
Are you sure about me?
No, I'm not sure about this. I'm very verbatim about not being sure about this. Right?
This is what I remember from these slides of Matthias Schöpfer.
Yeah.
He mentioned also Jahn-Teller was not, is not properly described by Born-Oppenheimer.
Yeah. Does this answer your question? Not enough, I guess. There's one more question, yeah?
Yeah, I have a similar question. So if we have a mixed system with like a metallic substrate and something grown on top of it, we need to have some smearing to account for the metal, but we also have something with a sharp gap on top of it. So what would you take, what kind of approach would you take in such a mixed system?
You have metals on molecules on metals, basically.
Yeah.
Yes. That depends on the degree of hybridization between the metal and the molecule. If the molecule is reasonably hybridized with the metal, you can take the metal, you can take the broadening without any problem. And if it's not hybridizing very strongly, then you shouldn't get density of states that originates from the molecule at the Fermi energy anyways. And if the density of states from the molecule that is at the Fermi energy, if the density of states of the molecule is not at the Fermi energy, then the broadening doesn't matter anyways for the molecule. And if you don't have hybridization but still have density of states at the Fermi energy, then you're fractionally occupying your molecular state. And that's typically happening spuriously as a result of delocalization error. So because you're using PBE. And the result here would be to use hybrid functionals. And I'm very glad to tell you more about this because I've looked into this issue quite a bit, but I think that would go beyond this talk at this point. Okay, Volker, how long can I talk?
5 minutes in principle.
No, we started late. Give me a break. Okay, Volker just tells me that I have to talk very, very quick. No. Yes. Okay, let me just finish what I wanted to say about metallic systems. The numerical implications for this is that the level switching is damped as much as we can, that we get much faster convergence. The negatives are that the total energy now depends on the broadening, that's called sigma here, and is no longer necessarily variational, which is also a bad thing. Fortunately, some kind of back extrapolation is possible typically, which I show in this graph here, where I've just increased Gaussian broadening for a copper 111 5-layer slab, and you can see that the total energy, once you correct them, is basically independent with some small error of the broadening, while the electronic free energy and the total energy corrected may change quite significantly. The absorption of molecules on metals is one of the major pitfalls. That was also already one of the questions. The physical implications that occur from the broadening is that some states become fractionally occupied, which is okay if you have bands, not okay if you have orbitals. In DFT, this is a well-defined ensemble average, but you need to make sure that you also interpret the results as such. Good. As a brief summary of the SCF, the ground state electron density is determined iteratively. The initial guess needs some initial thought and can change the results qualitatively. We have different ways to do density update, either by linear mixing or Pulay mixing, and can then further accelerate convergence using preconditioners or by broadening of the states. Now, the second part of my talk that I want to go into is structure optimization. Obviously, the first step when we do a calculation is we define some geometry guess, and then we relax the geometry into the ground state. Why is this actually important? It's important because even small changes of the structure can have huge changes on physical observables. The example that I have here is the charge carrier mobility in pentazine that is adsorbed on hexagonal boron nitride. And this has a first wetting layer that has essentially no charge carrier mobility at all. Then the first layer that forms a herringbone structure with a very oblique angle that has a small charge carrier mobility. And then the second layer grows in a different polymorphic form with a steeper angle where the mobility is about twice as large. And I could give you a lot of different examples where the actual details of the geometries change observables very strongly. There are two parts that come with structure search. One is global structure search, one is local structure search. Global structure search means we want to find for a given structure the lowest energy basin or the lowest energy structure. And this is something that I cannot talk about today, and this is something that I think Carsten will discuss in more detail. Yes, he agrees, at least qualitatively, I see. There are many different methods to do so that include, say, basin hopping, molecular dynamics, cluster expansion, recently machine learning, and much more, or many methods. Like I said, this is not something that I can go into detail today. Rather, I want to talk about local structure optimization. What does that mean? Local structure optimization is, let's assume we have found, at least qualitatively, the right basin. How do we find the correct bond lengths and bond angles? For these, again, we have, in principle, a lot of different methods available. In principle, we could just map out the potential energy surface. So let's say we try out every possible angle, every possible bond distance here, and see where the minimum is. Now, you're probably all familiar with the concept of configurational explosion. If you have more than just 2 degrees of freedom, you can't do that. That takes just way too many calculations. So this is something that is maybe done for dynamics, and even then it's typically done in a different way than that. In practice, this is basically never used. A second method that is also something that exists more in principle than in practice are so-called gradient-free methods. The way that they work is the following. You start by calculating 3 points. You determine the best and the worst energy. You remove the worst point, project via reflection the worst point over the connection of the 2 other points, and then you may expand or contract or compress somehow this length or the step that you want to go, and then you repeat that you repeat it until you actually find the minimum of your basin. That works in principle, and that's also a reasonably nice method that you can use for anything where you don't have the gradients. In practice, however, of course, we want to follow the gradients that are also often termed forces. Right. The forces are just the derivative of the total energy with respect to the nuclear coordinates. And the forces contain, in principle, 3 different terms. We need to differentiate with respect to the Hamiltonian and with respect to the 2 parts of the wave functions. Now, the first term basically only affects the nuclear-nuclear repulsion and the electron-nuclear repulsion. And is, well, illustrated here by this animation. We basically move the atoms while leaving the electron density constant. These are the so-called Hellman-Feynman forces, for which we have a nice and closed analytical expression. The other 2 forces are called the Pulay forces and are frequently said not to contribute at all, which is, I think, true for plane waves, but not necessarily true for localized basis sets, which we use, for example, in Ames, which is also used in Gaussian and other codes. They consist of 2 different contributions: the partial derivative with respect to the LCO coefficients and the derivative with respect to the orbitals themselves. The first contribution can be shown to vanish. The second term survives for atom-centered basis functions. There are then quite a bit of additional terms that contribute to the forces, for example, from the multiple expansion, from relativistic corrections, and also in some part from integration grids, especially if you take atom-centered integration grids. They are all straightforward. It's just mathematics that you have to apply, but they are lengthy, and I will not go through them. The question is, once we have the forces, how do we actually find the minimum? Because this is more relevant in practice. Basically, we could just follow the gradient. That's called basically steepest descent. We start from a point, and then we go some direction towards the biggest gradient until we actually are very close to the minimum. The problem is, once we are very close to the minimum, especially if it's a minimum that is not really parabolic but elliptical here, the steepest gradient may point to a direction that is not ideal. Right? In that case, you have a very strong curvature of the potential energy surface along the distance of the carbon-carbon bond in my example, while the bonding angle that you have here is a weak degree of freedom. And because the steepest descent is always along the carbon-carbon distance, you move only incrementally towards the correct value for the bond length. So this oscillates, it takes very long, and is very inconvenient. It's also not suitable for saddle points. I should mention at this point that, of course, improved versions exist, such as line minimization or conjugate gradient, which try to avoid this problem, but I'm also not going into details here. The second, what I want to discuss in a little bit more detail, if I'm still given the time, is that what we actually try to do is we approximate the potential energy surface by some kind of quadratic function. That is, we imply a model Hessian. And the model Hessian is, so we say that the total energy is given by the energy at the minimum distance plus then the first derivative times the displacement, and then we have the second derivative times the square of the displacement. This would be our, say, model Hessian. And then we try to find the minimum using what's called a quasi-Newton method. If you used a Newton method, we could actually calculate the exact Hessian and then go towards the minimum, but calculating the Hessian is typically too expensive, and instead we use what's called a quasi-Newton method. Quasi-Newton method works as following. This here is basically a description of the BFGS method. The idea is that you just calculate the gradient at any point in the potential energy surface and estimate the true Hessian. You start with a guess Hessian, then you calculate what the energy in the gradient is, and you use this gradient that is here shown as delta F to update the Hessian. What I wanted to say at this point, let me go back, is that the gas Hessian is something that is actually very important. And that is something that is typically not properly accounted for. Let me give you just one example here. The default gas Hessian that is used in most band structure codes is basically a diagonal matrix. So we don't really encode any information on it. And it's very easy to see that this is not necessarily a good idea. If you use this kind of gas Hessian, or the gas Hessian basically determines the step that your geometry optimization does, what kind of degrees of freedoms it explores. We had this one case where somebody calculates a molecule on the surface, and I would like to give you an example where this initial gas Hessian makes a big difference. I can't. Okay.
There's a button.
Yeah.
I can do that for you.
Thank you. So let's assume you have a surface, and you have a molecule, say an alphatic molecule. It's okay, leave it. That stands on top of it. If you use a diagonal matrix, so what would happen if you have a molecule that stands on top of it? Let me just draw it as a straight line. Because of van der Waals forces, usually the molecule will try to fall down, and that would be the most stable structure. Let's say the most stable structure looks actually like this, which is typically the case. If you start from the default initial gas from a diagonal matrix, the code will never explore this degree of freedom. It will maybe try to move some of the atoms here at the bottom because these experience a strong force, but these never experience a strong force because the reason why it fall over is just because the molecule wants to stay straight. And what will actually happen if you use a diagonal matrix is that you will end up with a molecule that looks somewhat curved like this. I unfortunately don't have the time to go into details here, but if you don't believe me, I urge you, take your favorite molecule on the surface and just change the initial gas for the Hessian, which you can do in AIMS actually. Right? So this is where I actually wanted to go. The default initial gas is typically unitary matrix, so that means it assumes that all degrees of freedoms contribute equally, which is typically not the case. We can do better than that by using what's called a Lind matrix, for example. That's a chemically motivated choice of coordinates where the total energy or where the potential energy surface has some parameters for the stretching of bonds, for the bending of angles, and also for the torsion of dihedral angles with pre-optimized parameters. This work actually, in my impression of course, or in my experience, this works reasonably well. There are still quite a few instances that I unfortunately can't discuss in detail right now, where a Lind Hessian is not good enough, and where you can actually start from what looks like a reasonable gas, where you would just have to tilt your molecule by a little bit, for example, that is not properly explored. Okay. And then, as I said before, once you have your initial Hessian, you still update it as the search progresses. The last, okay, Volker tells me to stop. Just two points that I want to make very quickly is what we still need to do when we use these quasi-harmonic approaches is to invoke some kind of line control or step length control. This we do basically by calculating the ratio between what we expect to get as energy range, as energy gain, and what is actually the true energy gain, and we can expand or reduce the step length accordingly. And this is one of the last pitfalls that I actually want to mention. If you do a geometry optimization, this is something you should repeatedly check, because what very frequently happens is that you start to explore a region that is not very good described in this harmonic approximation, and the step length becomes very, very, very small. And if that happens, not only does your calculation not progress anymore, also the energy doesn't change anymore. And it looks as if your calculation was converged, even though it isn't. It's just converged because the step length becomes so small. What you should do in this case is basically restart the calculation with a bigger step length. Okay, with this I'm at the conclusion. Local geometry optimizations are typically done by following the gradient, and quasi-Newton methods are the de facto standard. With this I stop here and thank you for your attention.